Today, we're building an NP chart together, step by step. It's one of the most widely used control charts for attribute data, and along the way, we'll cover all the fundamentals you need. For this hands-on session, we'll work inside the SIGMADESK Control Chart Generator, so everything you learn today, you learn by doing, and if you want to follow along, feel free to create an account and build your chart together with me. The sample dataset we're using today is also in the description below. Let's start from the home page. I open the Applications menu and choose Control Chart for Attributes and then NP Chart. This brings me straight to this simple interface. From here, there are two ways to get data in. I can paste my dataset directly into the spreadsheet, or I can load a control chart I saved before. I'll take the second route. Under the Chart Options section, I pick one of my saved charts and load it. You can save your study so your work is never lost. And the NP chart appears on the screen. But before moving on, let's take a quick look at the spreadsheet, in case you'd rather paste your own dataset here. The structure is simple. The first column holds the labels, and these appear along the x-axis of the chart. The second column is the number of defective units found in each sample group. And the third column is the sample size, which has to be identical in every row, because a constant sample size is the rule for the NP chart. I will make this clearer now. Before we start reading this chart, let's step back for a moment and understand the theory behind the NP chart. The NP chart monitors the number of defective units per subgroup, and it requires a constant sample size. That constant sample size is what makes it easy to build and to read. On screen, you can see a simple data set. For 10 days, we pulled exactly 100 units per day from final inspection, and we recorded the number of defective units each day. And across all 10 days, we found 50 defectives in total out of 1,000 units inspected. Now, let us build the chart from this data. The first thing we need is P-bar, the overall average proportion defective. The formula is total defectives divided by total units inspected. Applying it to our data, P-bar equals 50 divided by 1,000, which is 0.05. In other words, on average, 5% of our units are defective. Next, the center line. On an NP chart, the center line is N times P-bar, the expected number of defectives per subgroup. With our numbers, that is 100 times 0.05, which equals 5 defectives per day. This is basically the average number of defective units across the different subgroups, and you can verify it directly because 50 total defectives divided by 10 days also gives 5. So the center line sits at 5. Now the control limits. The formula is NP bar plus or minus 3 times the square root of NP bar times 1 minus P bar. Plugging in our numbers, that is 5 plus or minus 3 times the square root of 4.75. So the upper control limit is 11.54 and the lower control limit comes out negative. A count cannot be negative, so we set the lower limit to 0. That is the entire chart. Center line at 5, upper limit at 11.54, lower limit at 0. And we plot the daily defective counts directly. Any day with 12 or more defectives signals an out of control condition. With SIGMADESK, you never need to compute any of this by hand. The tool handles all the math behind the scenes. Let's back to SIGMADESK and check our real example with the larger dataset. We have 50 batches, and from each batch, exactly 100 units were inspected, so the constant sample size rule holds. SIGMADESK has already done all the math for us. The center line sits at 20.64, so on average, we found about 21 defective units per batch. The upper control limit is 32.78, and the lower control limit is 8.5. And notice the statistics panel. 5 points fall outside the control limit, and they are marked in red on the chart. 2 of them are early in the run. Up above the upper limit, around batch 5 and batch 6. Something clearly went wrong in those batches. And in a real investigation, those will be the first places to look. The other 3 red points are near the end, around batches 45 to 47, and they sit below the lower control limit. What makes the NP chart so valuable is how directly it answers one question. Is the number of defective units per batch stable over time? Whenever a point jumps above the upper control limit, as you see here, that sample group deserves attention because something out of the ordinary happened there. Perhaps a machine drifted, a material lot changed, or a new operator took over. And here's something people often miss. A point dropping below the lower control limit is also a signal worth chasing. Either your process genuinely improved, which is great news you'll want to understand and repeat, or your inspection missed some defects, which is a different problem entirely. And there we have it, all the details about the NP chart. If you want to keep practicing, the tool is waiting for you at SIGMADESK. And don't forget, you can also build all the other control chart types, as well as other quality tools like Gauge R and R, process capability analysis, and more. If you found this video helpful, consider the like button as a simple thank you. Subscribe for more Six Sigma content, and I'll see you in the next video.